The type checking rules that we need for polymorphism are very similar to the type checking rules that we already have for application. The big difference is they work at the type level instead of the term or expression level. First, a big fun expression with alpha over the expression e has type for all alpha tau, provided that the expression e has type tau inside of an extended environment. This notation on the left extends the current type environment, the new type variable. Next up, a type application is well typed, provided that the type we're supplying is valid and that the expression has a for all type, so it's expecting a type argument. If that expression E has type for all A, tau1, then the result type should be tau1, but every place where tau1 had an A, we should instead see the argument type tau0 substituted instead. So this notation here is for type substitution. Now, stepping back for 1 minute, this type validity judgment is going to check that tau0 has no free type variables inside of it. That judgment is down below. First, a type variable is valid, provided that the current environment has a binding for that variable. Second, a for all type is valid as long as the body, tau, is valid inside of an extended environment that now has a binding for A. These two rules are the most interesting ones for type validity. Any base type like int is automatically valid, and a composite type like arrow is valid as long as its component types are valid. And for an arrow, that means the left and right-hand sides both have to be valid. That's all we're going to say about the type checking rules. If you'd like to see how the rules on this slide translate into code, then take a look at the Split files for this class.